Welcome. Today, we are going to master Chapter 5, Systems of Equations. In this comprehensive session, we will cover all three core sections together. First, Section 5.1 introduces the foundational concept of systems of equations. Next, Section 5.2 explores the powerful algebraic tool known as the elimination method. Finally, Section 5.3 guides us through the practical applications of systems of equations. Let's master this entire chapter in this class. A system of linear equations consists of two or more linear equations in the same variables. Let's look at this system. The solution to this system is an ordered pair, x and y, that satisfies both equations simultaneously at the same time. By testing the values x equals 3 and y equals 2, we can verify it makes both equations true. Graphically, this unique solution represents the single point of intersection where the two lines cross. Let's practice solving a similar system of equations by graphing. Our system is x minus 2y equals negative 4 and 2x plus y equals 7. In step 1, we rewrite both equations in slope-intercept form to graph them. The first line transforms into y equals 1/2 x plus 2, passing through points 0, 2 and 2, 3. The second line becomes y equals negative 2x plus 7, passing through 2, 3 and 3, 1. In step 2, we plot them together and read the point of intersection, which is exactly 2, 3. Finally, in step 3, we substitute these coordinates back into both original equations to verify. Since both equations yield perfectly true statements, 2, 3 is our definitive solution. The substitution method involves more algebra than graphing, but it gives us highly accurate solutions. First, we take one equation and solve it for one variable, such as y. Next, we substitute this expression into the other equation, creating an equation with just one single variable. We solve for x and then substitute that value back to find our second variable. Let's trace this entire algebraic process step by step without any shortcuts. Let's solve a similar example using the graphing method. Our system consists of 3y plus x equals 9 and 3y plus 2x equals 12. In step 1, we isolate y to rewrite both equations in slope-intercept form. The first line becomes y equals negative 1/3 x plus 3, passing through points 0, 3 and 3, 2. The second line transforms into y equals negative 2/3 x plus 4, passing through 0, 4 and 3, 2. In step 2, plotting these lines reveals their unique point of intersection at exactly 3, 2. Finally, in step 3, we substitute x equals 3 and y equals 2 back into our original equations. Since both equations result in perfectly true statements, the pair 3, 2 is our final solution. So far, we have looked at systems with exactly one solution. However, some systems of linear equations have no solutions at all. A system of equations with no solutions is called an inconsistent system. Let's trace this system by graphing. When we convert both equations into slope-intercept form, we see that both lines have the exact same slope of -2, but different y-intercepts. Because their slopes are equal, the two lines are perfectly parallel and will never intersect. Since there is no point of intersection, the system has no solutions. Let's solve a dependent system of equations by graphing. Our new system is y plus 2x equals 3 and 3y plus 6x equals 9. First, let's rearrange both equations into slope-intercept form to find their points. Step 2. Let's graph both equations on the same coordinate plane. As you can see, both equations represent the exact same line. Therefore, the lines coincide completely, giving us infinitely many points of intersection. The system is dependent, having infinitely many solutions. When graphing is difficult or inaccurate, we use the elimination method. Let's solve our new system. Minus 2y plus 3x equals 8 and 4y minus x equals 4. Our first step is to make the coefficients of one variable have the same absolute value. Let's multiply the entire second equation by 3. 3 times the quantity 4y minus x equals 3 times 4. This gives us a new equivalent equation, 12y minus 3x equals 12. Step 2. Now add the two equations together to eliminate the variable x. Minus 2y plus 12y is 10y. The 3x and minus 3x cancel out to 0. And 8 plus 12 equals 20. Dividing by 10, we beautifully find y equals 2. Let's solve a system of linear equations with fractional coefficients. Our problem is 1 over 2a plus 2 over 3b equals 7 over 6, and 3 over 4a minus 1 over 2b equals 1 over 4. To make it simpler, we will clear the fractions by multiplying each equation by its least common multiple. Let's clear the fractions. Multiplying the first equation by 6 gives 3a plus 4b equals 7. Multiplying the second equation by 4 gives 3a minus 2b equals 1. Now we have a beautiful system of integer equations. Step 2. Notice that the coefficient of a is 3 in both equations. We can eliminate a by subtracting the second equation from the first. 3a minus 3a is 0. For b minus 2, b becomes 6b. And 7 minus 1 equals 6. Dividing both sides by 6, we get b equals 1. Step 3. Finally, substitute b equals 1 back into one of our integer equations. Let's use 3a minus 2b equals 1. Substituting b gives 3a minus 2 equals 1. Adding 2 to both sides, 3a equals 3. Which means it equals 1. Our final solution is it equals 1 and b equals 1. Let's solve an age word problem using systems of equations. The sum of Jose's and Elizabeth's current ages is 44 years. For years ago, Elizabeth was 5 times as old as Jose. Let's define x as Jose's current age and y as Elizabeth's current age. Step 1. Let's form our system of equations. Since the sum of their present ages is 44, our first equation is x plus y equals 44. For years ago, their ages were x minus 4 and y minus 4. Elizabeth was 5 times Jose's age, so y minus 4 equals 5 times the quantity x minus 4. Simplifying this gives our second equation, y minus 5x equals minus 16. Step 2. Let's align and solve the system of equations. Since the y coefficients are the same, we can eliminate y by subtracting the second equation from the first. Y minus y cancels out. X minus minus 5x becomes 6x. And 44 minus minus 16 beautifully equals 60. Dividing by 6, we find that x equals 10. Jose is 10 years old. Step 3. Now substitute x equals 10 back into our first original equation. 10 plus y equals 44. Subtracting 10 from both sides, we beautifully find y equals 34. Therefore, today, Jose is 10 years old and Elizabeth is 34 years old. We have successfully solved the Chapter 5 age problem. Let's solve a number word problem using the substitution method. The sum of two integers is 48. The larger number is 3 less than 4 times the smaller one. Let's define x as the smaller number and y as the larger number. Step 1. Let's write the system of equations. Since their sum is 48, our first equation is x plus y equals 48. The second condition tells us that y equals 4x minus 3. Because the second equation directly expresses y in terms of x, it makes perfect sense to use substitution. Step 2. Let's substitute 4x minus 3 for y in the first equation. This gives us x plus the quantity 4x minus 3 equals 48. Combining like terms, we get 5x minus 3 equals 48. Adding 3 to both sides gives 5x equals 50. Dividing both sides by 5, we perfectly find x equals 10. Step 3. Now substitute x equals 10 back into our second equation to find y. Y equals 4 times 10 minus 3. 4 times 10 is 40, and minus 3 gives 37. Therefore, the smaller number is 10, and the larger number is 37. We have successfully checked and solved this substitution problem. Let's solve a river current word problem. A rescue boat travels 90 miles downriver in 3 hours. Returning upriver, it takes 5 hours to travel the same 90 miles. Let's find the speed of the boat in still water and the speed of the current. Step 1. Let's form our equations using the formula, rate times time equals distance. When going downriver, the effective speed increases to be plus c. Multiplying by 3 hours gives 90 miles, which simplifies to be plus c equals 30. Upriver, the current fights the boat, making the speed be minus c. Multiplying by 5 hours gives 90 miles, simplifying to be minus c equals 18. Step 2. Let's solve the system by adding the two equations together. Since the current terms have opposite signs, they will cancel out. b plus b equals 2b. Positive c and negative c become 0. And 30 plus 18 equals 48. Dividing both sides by 2, we beautifully find that b equals 24 miles per hour. Step 3. Finally, let's substitute b equals 24 back into the first equation. 24 plus c equals 30. Subtracting 24 from both sides, we perfectly find c equals 6. So, the boat's speed in still water is 24 miles per hour, and the speed of the water current is 6 miles per hour. The motion problem is fully solved.